So we were reviewing what was going on last class, what happened last class. So we said that the characteristics that we need from the oscillator are a linear characteristic with respect to some voltage. So we want the output frequency to be a linear function of some input voltage, and then that would be embedded in a PLL to generate the LO signal that you want. Okay. Looking at the different types of VCOs, we are specifically interested in one kind of VCO, which is the LC oscillator, and we are going to look at this in a lot of detail. Now obviously, to do that we needed to understand the basic characteristics of an oscillator, what are the conditions under which some circuit would oscillate, and then move on to specifically how do you design an LC oscillator. Okay. The primary reason we want this LC oscillator is because it has very good phase noise, or rather very good spectral purity. We'll call it spectral purity for now because we don't know what phase noise is. Okay. But from the fact that you want to generate a very ideal tone or something which looks like an ideal tone, we should understand that any oscillator which does that is the one that we want. And since the LC oscillator looks like it could do that, as we saw last class, because of the frequency shaping from the LC resonance, we think that that may actually do better than some of these other kinds of oscillators that we are aware of. Now, to understand the basic operation of any oscillator, you need to understand the system level analysis of such a circuit and figure out what could make it potentially oscillate. And we saw last class that these are what are called the Barkhausen criteria. And if you take a feedback system, you can show that when the loop gain becomes greater than or equal to 1, at the point when the phase of the transfer function, phase of the loop gain goes to 360 degrees, at that point you can show that the system is potentially oscillatory. Okay. Now you should realize that any real function, these are actually small signal transfer functions we are talking about here. Any real system, one of you had a question about it yesterday after class. Obviously any real system, if what you actually require for stable oscillations are at the frequency when the phase goes to 360 degrees, you want the amplitude, the magnitude of the loop gain to go to exactly 1. That is when you have stable oscillations. If it is less than 1, your oscillations will start dying out. If it's greater than 1, your oscillations will start building up. So for stable oscillations, it needs to be exactly equal to 1. When we say greater than or equal to 1, what we mean is there is a potential for oscillatory behavior, and the amplitude, if the gain was larger than 1, the amplitude would keep increasing. The hope is that at some point of time, the system being inherently non-linear, when the amplitude keeps increasing, what will happen is at some point of time, the magnitude of the large signal loop gain will become equal to 1. Okay. Now this may not happen at the same frequency at which it started with the small signal transfer function, because the phase of the transfer function will also keep changing when the large signal transfer function changes. We saw a classic example where you have an oscillator, an RC oscillator. It starts up as an RC oscillator, but eventually it becomes what is called a ring oscillator with full swing. Okay, that is a classic case when actually the frequency is a strong function of the amplitude itself. Okay, we analyze different kinds of oscillators to figure out if these systems would oscillate or not. Obviously, the first couple of cases we took, they did not oscillate because you did not transfer the, you did not have satisfy the condition for phase shift and gain at the particular frequency that we are interested in. So the first one we took was an RC oscillator with a single stage. Then we took an RC oscillator with 2 stages. Both of these did not oscillate. So you need a minimum of, so actually the third one we took was an RC oscillator with 2 stages and an ideal inverter. But even this case, the phase shift you get, the excess phase shift of 180 degrees is obtained when the frequency reaches infinity. So even this particular system will not oscillate. So you really need a circuit like this, a 3-stage system, to get oscillatory behavior. And we took the case of an LC oscillator specifically, and we said the way we are going to realize this, you have some transfer function from the active circuit, and you are going to modify the feedback, okay, through a frequency selective network. We will soon see what that frequency selective network is, but really the simplest frequency selective network we could think of was an LC tank. Okay, and you will find that many of these circuits that we look at are either simple LC tanks or modifications of LC tanks. Okay, but we know that an LC tank has a frequency dependent, its impedance has a frequency dependent behavior, and therefore what we are going to do is maybe we take an amplifier and apply feedback using an LC tank and see what happens. Okay, so very specifically we said if you just had an LC circuit with some initial condition, let us say the initial condition could be current through the inductor or the voltage across the capacitor or a combination thereof. The easiest case to analyze is if you have a fixed voltage across the capacitor, because that will automatically tell you what the amplitude of the oscillations are going to be. Since the energy in the capacitor is sent into the inductor and vice versa over a period of time, you will get classic oscillatory behavior with the peak amplitude being equal to the initial charge across the capacitor. Okay, the frequency of oscillation will be equal to 1 over root LC. This also you have seen many times before. Okay, now if you take any practical oscillator, so now we are going to start analyzing these kinds of LC circuits. Now if you take any practical LC circuit, the inductor is going to come with some series resistance, and so is the capacitor. Okay, we are just replacing the or adding the most dominant parasitics in the inductor and the capacitor, and normally these are the series resistances, series losses. In reality you could have shunt losses in the inductor, shunt losses in the capacitor, and so on. We will look at this simplest behavior. So I'll call this L and the series resistance as RL. This is C and series resistance as RC. Now we know that you can perform a bunch of series to parallel conversions and in fact I'll call it LP, CP and RP. Okay, you can perform a series to parallel conversion and bring this to a parallel equivalent circuit. Okay, now what do you know about this parallel equivalent circuit? You know that the resonant frequency of this tank, the angular resonant frequency, is 1 over root LPCP. Okay, and you know that the losses in the tank are represented by the resistance RP. Okay, so RP represents the losses in the tank. Now, because we now have a way of looking at this LC tank as between a single pair of differential ports, okay, we are going to look at a slightly different way of viewing the oscillator. So far we have been looking at it as a feedback oscillator. In reality, or not in reality, in many of these LC oscillators, it is actually easier to view the oscillator in a slightly different fashion, what is called the one-port view of the oscillator. The basic idea is very simple. You are going to, so let us say this is the LC tank, okay, and normally we know that the LC tank has some losses which are represented by the shunt resistance RP. Okay, so now what we are going to say is, to build an oscillator, we are actually going to take an active circuit, okay, and connect it across the LC tank, okay, such that the active circuit is going to compensate for the losses in the LC tank to ensure that you have sustained oscillations. Understand? So now to do that, the active circuit needs to have some negative resistance RA. Okay, because that negative resistance needs to cancel out the positive resistance of the tank. Right? That is the only way to have sustained oscillations. Okay? So you know that for sustained oscillations or for stable oscillations, you need to have these two being equal in magnitude and opposite in sign, right? So you have minus RA coming from the active network. The magnitude of that minus RA should be the same as the magnitude of the losses in the tank. Okay. Now we know that in a real oscillator there are two stable conditions. One is when there are no oscillations, and the other stable condition is when there are oscillations. Right? You might actually have a case when there are no oscillations at all, the circuit will be biased up and everything will be fine. And that is in fact one of the stable conditions of this LC oscillator. If you don't have any initial condition, a stable condition is that there is nothing, there is no oscillation. Okay? So what you really need is something to actually start up the oscillation. What do you need if you have an RLC tank? What do you really need to start up the oscillation? You need some negative impedance which will overwhelm the positive impedance of the tank and actually give you oscillations which rise up from nothing or very close to nothing to some level of stable oscillation, right? So maybe your stable condition is this, okay? What you actually want at the end is oscillations of a particular amplitude. Okay, so in fact let me draw this like this. Okay, you actually want to go from here to here. Okay, what is the procedure for going from here to here? In any linear oscillator, the way to go from here to here is actually to get a bunch of increasing oscillations. So in other words, if you look at the envelope of this, you are going to get oscillations which slowly grow to reach the stable amplitude. What do you need? What condition do you need from this? So this is just a DC bias. These are stable oscillations and these are growing oscillations, right? We know what condition we need for this. That is very easy. We just need to bias up the circuit for the given conditions for oscillation, right? We need a minus RA. We know how to design, let us assume we know how to design a circuit which will give you minus RA. Okay? So that will have a certain bias point, certain transistor size and so on. We know the conditions for this. We have an LC oscillator. Frequency is given by 1 over root LC. Amplitude is given by minus RA equal to RP. That also we know. What do we know in this region? So we know that the loop gain should be greater than 1, okay, for growing oscillations. There are really many different ways of looking at it, right? We know that the loop gain should be greater than 1. What else do we know? We know that we saw yesterday that the poles, you need, first of all, for oscillatory behavior, right, for any, this is a second order system, right? You have an L and a C, you have a second order system, okay? For a second order system, to display oscillatory behavior, what are the conditions which are needed? For any random second order system, you need complex conjugate poles. When do you have complex conjugate poles in a second order system? With respect to the Q. When the Q is greater than half. Okay? For a second order system, okay, you have complex conjugate when Q is greater than half. Okay? And these complex conjugate poles could be either in the left half plane, the right half plane, or on the imaginary axis. right? In this particular case, for stable oscillations, you want them to be on the imaginary axis. Okay? If you want growing oscillations, you want them to be in the right half plane. Okay? Because the right half plane actually gives you a complex conjugate roots with the real part which will give you a growing exponential. Right? Okay? So let us say the poles were here, and as the oscillations grow, you want the poles to move left, okay, and the final stable oscillations, okay, you want them to be something like this. You want them to be complex conjugate poles on the imaginary axis, right? So this is what you need from the system. Now let us try to correlate this back to our one-port view of the oscillator, right? What do you have in the one-port view? You have certain losses represented by RP, and you have a certain negative input impedance from the active portion. So you want to correlate this to a relationship between minus RA and RP. We know that for stable oscillations, we need this condition. As it turns out, for a parallel RLC tank, for this condition, okay, so you need mod RA to be less than mod RP. Okay, if the negative portion, negative resistance portion is smaller in magnitude compared to the positive losses, positive resistance of the tank, then what happens is you will get a resultant negative part, and that resultant negative part will actually give you complex conjugate poles on the right half plane, and those will give you growing exponentials. However, you need this minus RA to be a function of, you want this minus RA, this negative resistance, to be a function of the output amplitude. The reason is, once the amplitude has actually grown to a particular point, you want it to be stable oscillations. And in any real circuit, you should understand that this will happen for one reason or the other, because the negative resistance will depend on some small signal parameters inside the active circuit. And as the amplitude grows, quite often the simplest case could be as the amplitude starts approaching the supply, you will find that it cannot grow beyond that, which means that the oscillation amplitude will necessarily be limited. There will be some other nonlinear process which actually takes over and limits the amplitude and limits the negative resistance. Okay? And we will look at some of these for LC oscillators. Okay? So now we have a good idea of what we need from the circuit. So we need to figure out an active circuit which gives us this negative impedance. Right? What kind of active circuit can you think of that gives us this negative impedance? As it turns out, there are actually many different kinds of active networks which can give you this negative resistance. Okay? In fact, we have seen some of them. When we actually did the LNA input impedance, we found that there are certain cases which can actually give you negative impedance. They are also negative frequency dependent impedances. But really we are looking for the simplest case. Okay? Now, before we look at the simplest case, we actually need to let's take a step back and look back at what we did for the RC oscillators. We started off with the simple one-stage RC oscillator and proceeded on to actually create our first oscillator that we realized. Okay, let us do the same thing with an LC oscillator. Now, so far we have said that we have a forward network, H of S, okay, and maybe a frequency dependent feedback network. Okay, the simplest example of that Okay, I'm going to take an RLC tank. I'm going to take the exact same circuit we had before. Earlier we just had an RC as the load. Now we are going to have an RLC as the load. Right? The transistor gives you some gain and the RLC tank actually gives you the frequency dependent feedback. So now I'm going to take this guy. Okay? So let us say I take this network. Will this oscillate? Why not? How do you figure out whether a circuit will oscillate or not? You need to look at the phase shift and you need to look at at what frequency the phase shift hits 360 degrees, and then you need to figure out what the gain of the circuit is at that frequency. In this particular case, the phase shift and the feedback is actually frequency dependent. Okay? So now we know that the feedback will happen only at or very close to frequencies of 1 over 2 pi root LC. Correct? Okay, so at 1 over 2 pi root LC, what is the phase shift of given by the tank? 0, right? It is purely resistive. What is the phase shift given by the transistor? There is a total phase of 180 degrees. So the total phase possible, okay, at frequencies where you can get some gain out of the circuit is only 180 degrees. Okay, so this circuit will never oscillate. (180 degrees) at omega equals 1 over root LC. Okay, so very obviously this circuit will never oscillate. Okay, this does not satisfy Barkhausen criteria. Okay, let us take the next circuit. What did we do? We moved from one stage to two stages. Let us do the same thing for this guy. Okay, so what I'm going to do is, I'm going to take a copy of this guy. Okay, I'm taking the output of the second guy and feeding it back to the input of the first guy. So this is RLC. Okay, what is the phase shift given by the first stage? At 1 over root LC, 180 degrees. What is the phase shift given by the second guy? 180 degrees. So the total phase shift around the loop at resonance is 360 degrees. So very good. So we have actually managed, even with a two stage, to actually create potential oscillatory behavior. So first of all, omega naught is 1 over root LC. Phase shift at omega naught 360 degrees. So this means potentially you could have oscillations. What is the condition that needs to be satisfied? The loop gain should be greater than or equal to 1. What is the loop gain in this case? GMR squared. GMR the whole squared. So loop gain is GMR the whole squared. Obviously the condition for oscillations is that at omega naught is 1 over root LC, you need to have this gain to be greater than or equal to 1. We know that preferably we want it to be greater than 1 for growing oscillations. Right? Okay, this is actually very good because we have just come up with an oscillator, with an LC oscillator, and the condition for oscillations is also quite straightforward. What you need to do is find out the losses in the tank, right? Find out the resistance, parallel resistance of the tank, and you design a GM for this particular condition and you are done. Right? And as it turns out, this particular circuit has one other advantage. We just said each stage actually gives you 180 degree phase shift. So let us say this was V1, this was V2, right? The nice thing about this, V1 and V2 are 180 degree out of phase shift, so you have just got a differential circuit, right? You have a circuit which actually gives you differential outputs, which is even better. Okay. So now, as it turns out, a popular way of redrawing this circuit is in a true differential form. We have drawn it like this. We started off with two identical stages. We figured out that the two outputs are at 180 degrees. Therefore, now it makes sense to actually redraw it in a differential form. So if you actually do that, so what do you know? Let's say this was M1. Let's say this was M2. Okay, look at the gate source drain connections of M1 and M2. If you look at M1, the drain connection is V1, the gate connection is V2. If you look at M2, the drain connection is V2 and the gate connection is V1. Right? So I'm just going to flip the MOSFET this way. Okay, so what I need to do is, let us say this was V1, this was V2, then I need to connect the gate of M1 to V2 and the gate of M2 to V1. Okay, this is obviously a purely symmetric circuit, and this gives us our true LC oscillator that we have been looking for. Okay. So we know the condition for GM to oscillate and so on. How do we reconcile this with the one port view of the oscillator? What do we need to do? To reconcile this with the one port view of the oscillator, okay, what we need to do is separate out the tank and the active portion. This is the active portion looking down, and looking up is the tank. Okay, and the condition we have is that okay, the condition that we have, we first need some negative resistance RA from this. Okay, so let's first figure out if this resistance is really negative or not. Okay, so really let's take only one half circuit. So what I'm doing is, I have a voltage V1 here, okay, and I have a voltage V2 which is minus V1. Remember, it's exactly symmetric but 180 degree out of phase shift, and I want to find out the input impedance here from this node. Can you guess what it might be? Minus 1 by GM. Why is that? Exactly. If you had your gate to drain connected, it would be 1 over GM. Now you are actually inverting the gate, so that actually gives you a minus 1 over GM input impedance. Okay. So if you look at this circuit, the differential input impedance is minus 2 over GM, because you have M1 and M2. Okay, and now you have a condition. We know the condition between minus RA and RP. What is the condition? For stable oscillations, okay, for stable oscillations, you need minus RA, this magnitude, to be equal to RP. Correct? What is minus RA? Magnitude of minus RA is 2 over GM, should be equal to RP. What is RP here? It's 2R. Okay? Because you are actually looking at RP between these two ports. So it is actually 2R. Correct? So the condition for this, obviously this should be the same condition as what we have derived before, and it actually is, right? The condition for stable oscillations in that case was that GMR should be equal to 1. Again, in this case, if you want growing oscillations, which you will always want to design GMR to be much greater than 1, or the magnitude of minus 2 over GM to be less than or equal to RP, okay, or okay, this condition you will need to satisfy for growing oscillations. Okay, so you will need a minimum amount of GM to sustain oscillations, and you will need a GM larger than that to actually have growing oscillations. Shouldn't that be? Because I used, this is the naming convention, I just used RP as the overall parallel resistance. You use it as either 2R, yeah, you can write it as 2R, okay, or as RP, doesn't matter. So that's why I said RP equals 2R. Okay, this is the convention I am using. But really there are different ways of writing this. Be very careful. Some people prefer to write the two tanks separately, the two resistances separately. Other people may prefer to write it as L by 2, R by 2, right, and 2C to actually still get an oscillation frequency of 1 over root LC. Be careful about what convention has been used. Okay. But now we have come up with a condition for oscillation. Okay. So well and good. If you really want, true oscillatory behavior, you need to ensure that GM is greater than or equal to 2 over RP or 1 over R, and hope that the growing oscillations will stop at some point of time. Right? Now, if you were to build such an oscillator, we actually need to get a good idea of what the output amplitude will be also. Okay, apart from the frequency. The frequency we have actually figured out. Apart from that, we also need to figure out what the output amplitude could be. How do you figure out the output amplitude? Okay. Okay. That is one way to do it. So he suggests maybe I'm going to plot, this is the amplitude, and I'm going to plot GM versus this amplitude. What happens at very low amplitudes? What will you have? You will have some GM equal to the small signal GM. What happens as the amplitude increases? How do you know that? As it turns out, it does fall down, but at this stage I don't expect that all of you will know that it will fall down, right? But if you actually plot the GM versus amplitude, you will find that it does something. Okay, it does fall, which is actually very good for you, because what you need to do is find out the point where GM reaches this magic number, and you will be fine. But you have to be a little bit careful. This will actually give you an approximate value of GM. Okay. Now, in reality, if you actually take this oscillator, let us go back to this guy. Okay. Remember that this circuit actually has positive feedback. The fact that you are actually getting minus 2 over GM means that the circuit has positive feedback. Okay. And that should also be obvious, right? You are actually taking the inverse of this and feeding it back to the gate. Now, this kind of circuit, when you have positive feedback, especially with oscillations, what you will find is, what do you know about positive feedback? Especially if the feedback is very strong. You are trying to give a GM larger than a certain value. What happens is, in such a case, this positive feedback will actually try to make the transistor switch very strongly. Okay. In this particular case, you are actually trying to make the transistor turn on and turn off, right? When oscillations are happening on one side, let us take oscillations on this side are like this, and oscillations on this side are like this. Okay? Let us take this region of the operation. Look at the gate of M2. Gate of M2 is high. That means M2 is on. Okay? The gate of M1 is low. So this positive feedback, what it will tend to do, it will tend to turn off M1 very fast and very strongly, and it will tend to turn on M2 very fast and very strongly. Okay? Which means if you actually look at the oscillation period, especially in this large signal with a large signal amplitude, what you will find is the transistor actually experiences not only the saturation region, it actually moves from off to saturation and probably triode in between also. Okay, so to actually think that you can actually have a small signal analysis of such a circuit is definitely going to be wrong. Okay. Second thing is, if you think that you can actually correlate this some kind of small signal GM to the losses in the tank, that would also be in reality wrong. What you're actually trying to do is replenish the overall losses in one period. That is the best you can do. During part of that period, the transistor is off. Other part of the period, transistor is in saturation, maybe also in triode. Okay. So during this period, during some time it may actually give extra, energy into the tank. Maybe at some other time it actually draws. Maybe at some other time it doesn't do anything. Okay, that is possible. But overall, in one period with stable oscillations, you know that the losses are going to be replenished and give you stable oscillations. So that is actually a big difference between large signal operation and small signal operation. If you actually had small signal operation, you are assuming that the transistor stays in saturation throughout the period. Okay, you can actually come up with an proper negative resistance and correlate it to the resistance of the tank. Okay. Okay. Now one last thing, if you actually want to figure out at what amplitude the oscillator is going to end up at, we can actually come up with some approximations. Let us assume, for example, that the GM is very large, much larger than the minimum amount that you need. Okay, let us assume that. What does that mean? That means that the positive feedback is very strong, and that really means that the transistors are going to switch even better, right? So if you were to plot, you have a class after this, any of you? Okay, so just give me 2 more minutes. If you were actually to plot the current through this pair, okay, and let's say this is I1 and I2. We are actually interested maybe in the differential current ID. Okay. If you are actually to plot the current through M1 and M2, what will it look like? We said that the GM is very strong, and if the oscillations look like this, okay, we say that in this period, okay, M2 on and M1 off, right? Because of the strong positive feedback, we can say that the transistors will switch almost instantaneously, and therefore pretty much at this instant, okay, M1 will transition from on to off and M2 will transition from off to on, and very quickly, such that this is a very small fraction of the overall oscillation period. Is that understood? And I can say the same thing in this region. M1 is on, M2 is off. Okay. What does that mean for the for the current through the transistor? Correct. So if you actually plot the current, if you limit the current, it will look like a square wave. As we have drawn it, we have not shown the biasing details, so we don't know that the current is limited. So now let us add one more level of detail. So let me say I have some tail current IT. The signal picture is exactly the same. This is a differential circuit. This will be a virtual ground. So as far as the signal picture is concerned, this will be exactly the same. But now I am going to limit the current through the oscillator to be equal to IT at all times. If I do this and I plot the current through M1, let us say, so let us say I am plotting I1 as a function of time. Okay, what will this look like? With the phase I have drawn, M1 is off, so I will get 0 current. Okay, during the next half period, I will get IT. So the current through M1 will toggle between I0 and IT. And I can of course plot the current through M2. It will look like exactly the inverse of this. If I plot I2, okay, something like this. It will go between 0 and IT. Agree? So what I need to do is, I have actually figured out the current going through M1 and M2. Now to actually figure out the output voltage, what I need to do is take this current waveform. So in other words, what I am saying is, so ID is I1 minus I2, okay, and I need to pass this current waveform, the switching current waveform, through the parallel RLC tank. Okay, but in reality we have drawn it differently, so I will draw it the same way. Okay, this is RLC. This is the convention that we have taken. Okay, so it actually passes through an RLC tank in this fashion, right? So maybe I can even take the single-ended version and analyze it and double that amplitude to get the differential version, right? Because if I'm just interested in V1, maybe I can just take half of this. Okay, so that may actually be easier. So what I'll do is, I'll just take the single-ended version. Maybe I'll just take I1, which goes between 0 and IT. I don't need this portion at all. And what I am interested in is V1, right? I know that 2V1 will be the amplitude. It goes between V1 and minus V1. If I take V1 minus V2, that will be the output differential amplitude. What is this now? This is a switching current which is being passed through an RLC tank. I know that the RLC tank has a frequency shaping characteristic. So first I need to find out the frequency component in this switching waveform. Then I need to find out the component around omega naught is 1 over root LC and figure out what the amplitude is. Because at omega naught equal to 1 over root LC, I know that the resistance is R, right? So if I look at this, what is the Fourier series of this I1? So first of all, it's IT times, what is the DC value? Half IT. So DC value should be half, plus what is the second harmonic is, for a full square wave minus 1 to 1, it is 2 over pi. For this particular case, it will be 1 over pi. Okay, it will be 1 over pi times in this particular case I have 0 first and then this thing. So will it be a sine or a cosine? My square wave looks like this for I1, right? Will it be a sine or a cosine? It will be a minus sign, right? But at the end of the day we are interested in the magnitude, so let us say we write it like this, but it will actually be a minus sign. Okay, so maybe we'll even minus 1 over pi sine what? Omega naught 1 over root LC, because the period of the switching waveform, we have not indicated that, but the is 1 over 1 over f naught. Okay, the period of this is the same as the frequency of the fundamental that we are interested in. because we know that the transistors are switching at the same rate. Sine omega naught t, okay, plus so on. You'll also have the, obviously you'll have the third harmonic, fifth harmonic and so on. We'll ignore that for now. What we know about the LC tank is that it selectively shapes only the component around omega naught, okay. So V1 will be equal to IT times 1 over pi. So this is the magnitude of V1. IT times 1 over pi times R. Correct? So this I'll say select of I1. Select only the omega naught component of I1, and therefore the amplitude V1, magnitude of that will be IT times 1 over pi times R, which means the output differential is going to be 2 by pi times IT times R. Okay? So the output amplitude is 2 by pi times IT times R. Do you notice anything interesting about this? Correct. It looks something like a mixer, correct? And at the end of the day, that's what you're doing, right? Because the switching pair, this differential pair M1, M2, is actually, because the output is oscillating, it is actually switching at the rate of omega naught. And the current through the tail is IT, that is like a signal current. In an upconversion mixer, a baseband signal would have gone there. Here you only have a DC that is actually getting upconverted to F0, and you are actually, here in this case, you are actually shaping it with the tank. You are getting something which is like, which looks like a mixer. Anything else? Another interesting thing about this is that the output amplitude is not a function of the device at all. Do you find that strange? You have designed the device for a particular GM, maybe some large signal GM also, but somehow the amplitude is not a function of the device width at all. It is a function of only the bias current and the resistance of the tank. Do you find that surprising? So in other words, what I mean is, I take a current, I take an oscillator, I have designed it well, and I have a size, let us say, of 100 microns by 130 nanometers. Or 100 microns by 90 nanometers. We are using the 90 nanometers, right? Let's say 100 micron is the width and 90 nanometer is the length. Okay? I take the same oscillator, I just double the width. I make it 200 microns by 90 nanometers. The output amplitude doesn't change at all. Startup condition is different. It is startup faster. Right? It is startup faster. That is understood. But somehow the stable state doesn't change at all. Correct? But I'm saying I just changed GM, small signal GM, but somehow the large signal GM didn't change at all. Correct. This is because we have actually put a limit on the amount of current. Okay. So suppose I were to plot, okay, think about this, we'll discuss this on Friday's class, but suppose I were to actually plot the output amplitude as a function of device size. Okay. So think about what that will look like. The next thing is what will be the output amplitude as a function of current. These two things we need to find out. Okay. So I took the simple example of, let's say I had 100 microns and 200 microns. It looked like the output amplitude will not change at all. Okay. So I want you to think about whether it will never be a function of the width at all, or whether it could be a function of the width but maybe a weak function or something else. And we'll discuss that on Friday.